Well, good evening. Wonky Astronomer here. I'm just going to check if my sound's working on the stream. Well, good evening. It is. It is working. Welcome, viewers. We have a few viewers at the moment. More than I expected, actually. Just checking Facebook. All right. Well, we're here to have a look at this planet killer asteroid. What's it called? It's called 2011 UL21. And this is a rather large asteroid, perhaps 2.3 kilometers in diameter. And it's one of the largest potentially hazardous asteroids that, comes quite close to Earth. Now, back in 2011, when it was discovered, it was thought to have a 1 in a million chance of impacting the Earth in 2029. But since then, fortunately, that's been ruled out with subsequent observations. Just let me turn on my observatory camera there. So anyway, let's get to it. Let's find this asteroid. I haven't put my telescope on it in advance. I thought I'll do that as part of the stream. Greetings, Abe Bafola. Hope I'm pronouncing that right. We also have Locrian 7 saying hello in katakana. Do I know Locrian 7? Because I do know quite a few Japanese people. My wife is Japanese. But don't expect me to read. See, there was another comment here in hiragana. I think this says it's happening soon, something like that. But I had to use Google Translate for that. So don't expect me to read the Japanese comments. All right, let's do it. Let's find this asteroid. I'll just show you my my full screen. This is the screen that I'm seeing. But for the purposes of the stream, most of the time I will have a simpler view, which is not working right now. Oh, I know what I'm doing wrong. See, it's just my incompetence. Yeah, I'll have this simpler view. I might as well just tell you what all this is. My mouse pointer's there. So on the left there, that is the actual view through my telescope. That is a live view. You can see stars there. On the top here, well, that's me there. But to the right of my head there is a view of my telescope in the dome. I'm in the house, of course, controlling it from in here. I don't like to be out in the cold dome. There is I don't know if that's an emoji, from Priyanka Taylor. It's a little image. Don't think it's an emoji. I don't know what it means. Yeah, and then the top right there, we have a view of the sky. That's an all-sky camera, so I can see if it gets cloudy. Now, the forecast for tonight is pretty good, so I don't think we'll have a problem there. But you can see this is showing, what is it showing? It's showing the last 1 hour. And so you can see the stars there moving in that image. Then below that, we have the UFO counter. I'm hoping to see some UFOs tonight. And I'll be counting them like this. I want to just check if my sound effects are coming through. Okay. And then to the left of the UFO counter, we have some basic information about the asteroid. That is real time. It'll sometimes not display when I'm doing stuff with the app, but it's showing in particular, the distance there in real time. So it might change during the stream. It's now 0.044735 AU. That's astronomical units. An astronomical unit is the average distance between the Earth and the Sun. It's also there in millions of kilometers, 6.7 million. I don't think that'll change during the stream. Lochrin7 asks, what time is it for you? It's just after 9 p.m. here. I'm on Sydney time, which is GMT plus 10 hours. And it's a good night. I'm doing it now, even though the asteroid won't reach closest approach for another about 9 hours. But for me, it'll be below the horizon then. And it actually will go below my horizon, below the trees at about 11, so in about 2 hours. So that's why I have to do it now. But there's not much difference. It won't be much closer in 9 hours. It'll be, I think, instead of 6.7 million kilometers, it'll be 6.6 million. But the main thing is it'll be close enough that it will move fairly quickly across the view. Probably not fast enough to see just by looking at it, but if you look at it every minute or so, you should notice a little bit of difference. And I've got a new feature here that I just implemented today. That is the red arrow. I can place a red arrow. Hang on, can I move that? Right, I can move the red arrow. I can point it at a star, or I'll point it at this asteroid. I've also got a red circle. So we'll be able to notice the motion. All right. Another comment there. Which time can we see the asteroid? Well, I'm going to show it to you right now in the next few minutes. So you can see stars there in the in telescope view. So what I'm going to do is on my app here, this shows where the telescope's pointing right now. Those red circles there show where it's pointing. It's just to the left of the South Pole, South Celestial Pole, which is where the axis of the Earth goes through. So what I'm going to do now is find this asteroid. Got to bring up my observing list, which you can't see, but I'll move to the asteroid. There it is. I'll just change that grid to be horizon coordinates. And we zoom out, we can see roughly where it is. So it's, that's west. There's the asteroid. This sort of brown line is my horizon. That's trees and houses and things. And it is going down. In a couple of hours, it'll drop below that horizon. And over here is where my telescope's currently pointing. Now, what I usually do to improve the accuracy is I will choose a bright star nearby. I'll choose that one. It's called CRAS. And I'll center that, and I'll send the telescope to that first to check the accuracy. All right, so what I might do is bring up the view of the telescope in the dome. And I'm now going to send the telescope to that. Turn on the sound. You'll hear the sound from the dome. Okay. Here it goes. And you'll see the stars move, the telescope move, if all goes well. So the telescope's moving, and the dome is following it. The telescope has now finished moving, but the dome hasn't quite caught up. We're seeing white there because we're just seeing the inside of the dome. Okay, it's almost there. Should start to see stars. Oh, look at that. That star is basically right in the middle. I'm surprised. It's usually not in the middle. Okay. So usually what I do is I have to adjust it a bit to get that star right in the middle. And then I tell it synchronize to target, which means, I'm telling the telescope, you're pointing in the right direction. And Lockgreen 7 says, cool. Sorry. Yep, it's very cool. Okay, so now let me go back to this view. You can see I'm pointing here at this star called CRAS, and the asteroid we're interested in is here, so very close. So the telescope won't have to move very far. So I will now center on that and hit the button, and the telescope will move again. Okay. Now, dome's catching up. I think I'll just turn off the sound from the dome there. You're just hearing the fans and the motors and things in the dome. And sometimes, if there are animals around, you'll hear those as well through that security camera microphone. Now, hopefully, one of those stars there is the asteroid, but which one? Now I will zoom in. That rectangle there represents my field of view of the camera over there. Now it's oriented the wrong way. And to fix that, I'll change the coordinate system to equatorial. And okay, immediately I see there's a bright star there, which must be that one. There's a couple of stars there, which must be those two. So, okay, I think, let me zoom in a bit more. Now, there's two stars there, which correspond to those two. And just to their right, that's where it should be. So I think it's that one. That's what I think. Now, let me adjust the exposure a little bit. You can bring up the exposure. That's not bad, actually. Just playing with the camera exposure. Okay. So what I'm going to do is I'll center that. Actually, I might put it a little bit to the right of center. I'm just moving the telescope a little bit. How can we confirm that that really is, that one really is the asteroid? So what we will do, I'll put the red arrow on it. So we put the red arrow on it. And see if the red arrow stays on it. If it doesn't, that means it's the asteroid. It's really moving. Now, in fact, what I might do is I'll just take a couple of screenshots. Throughout this session, I might take a few screenshots. Just so I can see later how it moved. I think it's moved already, right? It's definitely gone off the red arrow. Now, I need to check whether it's that asteroid moving, or is it the whole, all the stars as well, if my telescope's not accurate. Now, what you can note is there's three stars, well, there's two stars there, and they form a straight line with this one that we think is the asteroid. Okay, I might put the red circle on it instead. There's the red circle. I'll put it in the middle of the red circle. Yeah, so that they're forming a straight line. Now, if that asteroid's moving, they won't form a straight line for long. In fact, I think already it's not a straight line anymore. So I think we found it. Now, last night let me put the data back, basic information. Last night I had a look at this asteroid. I recorded a video of it, made a time lapse. Let's see, can I show that? There it is. So this is the video I recorded last night. And this is bottom right of the screen I'm looking. As I skim through that video, you can see that object moving from right to left and back again. So that's what it looked like last night. I had a bit of a cloud coming through, so it wasn't ideal conditions. Tonight, it's much better. And yeah, look at it now. Look how much it's moved. I had that in the center of the circle. Now it's nearly to the edge in just that short time. Now that's because the got some more Japanese comments. I think that's hello in katakana. And this comment, I can't read that. That's got kanji in it. I'll check it later. I'll translate it later. Or just tell me what it means. Yep, that has moved quite a bit. So I'll recenter it. It's getting... I think I can actually see it moving second to second very slowly. Interesting. We have 12 viewers. It's more than I expected. Now, as I said, this asteroid is approaching to within 6.6 million kilometers. It's still like 19 times further than the moon. So it's still quite a distance away. It's traveling at about 26 kilometers per second through space, which is the same as 93,000 kilometers per hour. Oh, look, it's just passing that star now. Having trouble moving my red circle. Those two objects are merging. It's just going almost in front of that star. When it's close to another star, you can see the motion. You know, it's more obvious. Okay, I'm going to take another screenshot. You can't see these screenshots, but I may use them later. Okay, now the last close approach of this asteroid was, well, depends what you mean by close, but a comparable closeness was 110 years ago, or 109, 1915, when it came to within 11 million kilometers. Now, see, I'm having trouble keeping this circle on it. It's moving so fast. Now, the next very close approach of this one will be in 2089, and it'll come to within 2.7 million kilometers. Ooh. Wait a minute. Locrian 7, I'm asking if that is a name. Can speak Japanese. Okay. And how fast is the asteroid going? Yes. Well, I was answering that even before I saw the question. This is cool from Ashley. Thank you. Yeah, so it's traveling at 26 kilometers per second, as I said. Asteroids generally travel about 17 kilometers per second if they're in the main asteroid belt. Now, I might show some, let's see, show a couple of pictures. That is a depiction of the solar system, or the inner solar system, with sun in the middle, of course. Then you've got the planets circling it, Mercury, or orbiting it, sorry, Mercury, Venus, then Earth, then Mars. And then there's this belt of asteroids called the main asteroid belt. And then you've got Jupiter, and there's a couple of groups of asteroids that follow Jupiter's orbit ahead of and behind it. And this particular asteroid does not stick to any of those positions. This one comes in and crosses the Earth's orbit. Now, there's a question from Nilesh. Is this asteroid? Is this the asteroid, I guess you mean? And from Retronix, is it visible to the naked eye? I'll just center the circle again. The object in that red circle is the asteroid, and you can see it moving. Have to keep moving the circle. And it is not visible to the naked eye. If we look at the data here, you can see the visual magnitude is plus 12.1. And the way magnitudes work is, when they were first devised, people said, well, got a bunch of bright stars, we'll call them magnitude 1. And then stars are a little bit dimmer, we'll call them magnitude 2. And the ones dimmer than that are 3, and so on, down to 6, right? So the stars that are visible to the naked eye go down to about magnitude 6, and the higher numbers mean dimmer. So this is magnitude 12, so that's 6 magnitudes dimmer than the dimmest you can see with your naked eye. That represents about 200 times dimmer than the dimmest naked eye star you can see. But it's easily seen in my telescope. Moving the red circle again. So what I might do is have a look at the orbit of this asteroid, if I can bring that up. Okay, what I'll do is bring up a browser. This is the Jet Propulsion Laboratory Small Body Database. It's the database of small bodies. And this asteroid, as most asteroids are, well, all of them are actually, they're small bodies. And what we can do here is look at, well, there's a lot of data there, but there's a thing here called Orbit Viewer. And what we can do there is look at the orbit. This diagram shows the orbits of, let's see, Mercury there, the pink one, then Venus, then Earth is the blue one, and then the red one is Mars. And this line here is the orbit of the asteroid. And we can turn on, that's quite fast, hang on. Let's make it a bit slower. This is going backwards now. I've gone too far now. I've made it too slow. Yeah, I'm just going backwards to the point where it comes close to Earth, which I think is about there. Right. So now I'll run it forward. Now we can change the angle here. You can see that the orbit of that asteroid is very tilted compared to the Earth's orbit. Cool simulation. Thank you, Locrian7. Locrian, by the way, is a musical mode. I am aware of it. Yeah, so I'll play that forward again at moderate speed. And you can see the Earth there and the asteroid coming very close together. So that's where we are now, where it's very close to the Earth. And then it will head off. And as you can see, the orbit is tilted, so it'll go off to the north of the orbits of most of the planets. The planets tend to be in, pretty flat disk, but a lot of minor objects like asteroids and comets tend to have tilted orbits. Now, got to move my red circle again. Hang on, which one is it? I've lost track of which one it is. It's one of those three. I think it's the middle one. I could be wrong. Yeah, I think it's the middle one. I think I'd see it moving. What would happen if the asteroid hit the Earth? Now, that's a very good question. And I can show you some pictures of what that might look like. It might look like that. Or it might look like that. However, these pictures show, I think, a much bigger asteroid. This one would be perhaps 1,000 kilometers across. The one we're looking at is only maximum 4 kilometers across. Right. Richard says it's the middle star. Yes. The middle, well, it's not a star, but the middle thing that looks like a star. Now, pretty soon that's going to go off the edge, so I might have to move my telescope a little. Actually, I'll just take another screenshot. Okay. You can't see that screenshot. Now, I haven't seen any UFOs yet either. My UFO counter is still on 0, which is very disappointing. But of course, I might be looking away when one goes through. Okay, so I might have to just adjust this position because it's going to get close to the edge, right? We don't want it to disappear off the edge. So I'll put it back towards the lower right.
Occultation alert. 4 hours.
An occultation alert. I should have turned that off. It's in 4 hours. I don't need to know about it right now. Okay, so let me turn on my red circle again and put it. Hang on, which one is it? Oh, I think it's that one. That bright one in the circle. It's very close to a dimmer one, a dimmer star there, and you'll see them get closer together. An alarm on my phone just went off. So, but to answer that question, oh, wait a minute. Every time you jump, you move a billionth the width of a hydrogen atom, basically nothing, but still can be calculated. Yeah, I guess you mean that, you know, everything affects everything else gravitationally. Yep, that's it. It's moving in that circle. Now, yeah, to answer that earlier question about what would happen, I think I have a web page here that talks about that. Just a moment. Right. So, of course, the effect of an asteroid, if it hit the Earth, would depend a lot on how big it is and how fast it's going. So I've got a web page here that talks about that. How big must a space rock to be? How big must a space rock be to end human civilization? That's what we all want to know. And so it talks about some various examples. So the Chelyabinsk event, this was an event that happened in 2013 in Russia. It was about 20 meters in size, came down, injured 1,600 people and damaged buildings. Only small pieces of it reached the ground. Most of it burned up in the atmosphere. Well, maybe more of it did reach the ground, but it wasn't found. Very interesting how people got injured in that event. Let me just move my circle again. So this bus-sized asteroid came into the atmosphere, made a huge flash. It was captured on a lot of dash cams. A lot of people in Russia have dash cams, and made a really bright flash, but no sound initially because the sound takes longer to travel. And people inside saw this really bright light coming through their windows, so they went to their windows to have a look out to see what was going on. And while they're looking out their windows, the shockwave arrived. Bang! And all these windows shattered. So most of those people got injured by shards of broken glass from standing in front of a window when it shattered. I don't know if before that event, if that had been considered as a way that people would get injured by a big event like that. Now, okay, another big event was in the Tunguska event. A 50-meter wide object struck the Earth in, when was it? 1908. 50 meters, so the size of an Olympic pool. That one was probably a comet, and it flattened 80 million trees over a 2,000 square kilometer area. There is a picture of some of the flattened trees. Now, then we have the example of a 330-foot or 100-meter asteroid, size of a soccer field, and that would destroy buildings up to 15 kilometers away, shatter windows 100 kilometers away, and trigger earthquakes and eject debris into the air that would remain in the air. So you're starting to get into the realms of perhaps a mini nuclear winter. Now, an even bigger one, 160 meters. It's using an actual asteroid as an example there, one that hasn't hit the Earth, but if it did, 160 meters, that would create a crater 1.6 kilometers wide and 370 meters deep. If it hit the ocean, you'd have huge tsunamis. If it fell on London, for example, you'd have broken windows over the whole of southeast England, and there'd be no survivors in the center of the city. That is what is that? That's an example of a 160 meter object. What time can we see it from Japan? And also, what time can we see from India? Well, Japan, you can probably, wait a minute, let me check the declination. It's minus 28. It might be difficult to see from Japan because this is in the south. You might see it low in the south, and you'd see it at about the same time because we are on roughly the same longitude, Japan and Sydney. So you'd see it around, in the early evening. India, let's see, India's further west. Yep, I think you'd see it through most of the night in India. But you'd have to look it up in an app that shows asteroids. Now, wild out Aussie, even if you were moving through space at 99% of the speed of light, it would appear still just like that image. Yeah, I guess so. My circle needs moving again. I think that's it. So finally, a 780 meter object. I think that image there is much bigger. That's showing an impact much bigger than 780 meters. That's less than 1 kilometer, but that image looks like a few hundred kilometers. You'd get a crater 11 kilometers wide and 600 meters deep. It'd cause magnitude 7.5 earthquakes up to 500 kilometers from the impact site, and you'd have windows shattered 1,600 kilometers away. Right, so that's 780 meters. Now this object is, what is it, 2.3 kilometers, perhaps. That's about 3 times 780 meters. So this would do even more damage. That's why they call it a planet killer. Equal to how much tons of TNT? That's a good question. Just a moment. I think, they usually mention Hiroshima as a reference. It is mentioned. The Chelyabinsk event, which was a 20-meter object, that was about 10 times as much energy as the Hiroshima bomb. I don't know how many kilotons. That was kilotons of TNT, the Hiroshima bomb, not megatons. You'd have to look that up. All right. Now, I have to move my circle again. It's getting it's quite an arduous task keeping this circle around the asteroid. Now, I should just explain the differences between the various types of objects, because these names are a bit confusing. You've got meteoroids, meteors, meteorites, comets, and asteroids. What's the difference? So meteoroids and asteroids are floating in space, orbiting the sun, and the difference is meteoroids are smaller than 1 meter and asteroids are bigger than 1 meter. And they're usually either rocky or metallic. They can have a lot of iron in them. Now, if a small object, such as a meteoroid, enters the atmosphere of the Earth, it creates a bright streak as it heats up, and that's a meteor. So once it's in the atmosphere, it's a meteor. Now, most meteors are very small, like grains of sand, but they can be up to 1 meter. But they normally burn up in the atmosphere. And they usually come from, they're the debris left by comets. Usually the tails of comets leave trails of small particles. And if the Earth passes through that trail, those objects hit the atmosphere, and when we see them as meteors. Now, a meteorite is a rock from space that reaches the ground. So, as I said, most meteors burn up in the atmosphere, so they vaporize. So you don't find them on the ground, but if they do reach the ground, they become meteorites. Now, a comet is similar to a meteoroid, but it's usually icy, and it contains gases, various gases, typically methane. And as it gets close to the sun, it will, those gases and materials, dust as well, will be blown off by the added heat, and that causes the comet's tail. Comets usually also have orbits that are very elongated, so they go a long way from the sun and then come back in close to the sun. That's when they get a tail. Some of them don't come back though. And then an asteroid is a rock or a metallic object that's bigger than 1 meter. So it's like a meteoroid, but bigger. And most of them, as I said, are located between the orbits of Mars and Jupiter, but some of them stray into Earth's orbit. What do we have here? Hang on. Right, I saw that comment. It's moving out of the circle, yes. As I said, it's a very arduous job keeping it in the circle. I wish I could automate this. Now, of course, I'm showing a picture there of a asteroid impacting the Earth. It looks very bad, and fortunately, I believe there are no planet killer asteroids, or put it this way, we've already found, we believe, all the asteroids that are big enough to destroy civilization, and we know that none of them are going to hit the Earth in the next 1,000 years. Now, there could be some smaller ones that will hit the Earth or are due to hit the Earth, but they won't destroy all of civilization. They might cause a lot of damage. Move the circle again. And but interestingly, asteroid impacts, although they can be very devastating, it is the one natural disaster that we can potentially stop from happening, because we can predict if an object's going to hit the Earth, and we can send a spacecraft to stop it. Something the dinosaurs couldn't do. And in fact, a spacecraft was sent to an asteroid, the binary asteroid Didymos and Dimorphos, and they crashed a spacecraft into the smaller one, which is the moon of Didymos, right? Dimorphos is the moon, I think. So they crashed one into Dimorphos and measured how much its orbit around Didymos was changed. And, you know, they changed it quite a bit, more than they expected, which means we probably can deflect an asteroid if it's heading towards the Earth. I think I've seen a recording of craft hitting a space object. Yeah, there is a video. So I should have prepared this to show, but yeah, there's a video taken from that spacecraft as it comes in and crashes into that little asteroid. So there it is in a circle. Now, I think we've seen enough. But before I end the stream, I'll just mention that I've got another stream scheduled for 2 nights from now, Saturday night here at, I think it's 11 p.m, because there's another asteroid which is making a close approach. It's called, what's it called? 2024 MK. 2024 MK. And that one was only discovered on June 16th, just a couple of weeks ago. The names of asteroids, or these designations that we're using, the first part is the year that it was discovered. So this one's called 2011 UL21, so it was discovered in 2011. This other one, 2024 MK, was just discovered this year, a couple of weeks ago, and it is going to pass much, much closer than this one. It's going to pass closer than the moon, This is, as I said, about 19 times further than the moon. But the one on Saturday is going to pass closer than the moon. It's not going to hit us. It is a smaller asteroid. How big is it? I haven't got the data here. It's probably like 100, maybe 200 meters. So quite a bit smaller than this, about 10 times smaller. So yeah, I've scheduled a stream for that. Now, because that's much closer, it will appear to move much faster than this one. I actually had a look at it last night, and it was moving. It was moving so fast. Oh, wait a minute. Did I look at it? Maybe I didn't look at it. No, I looked at a simulation. That's right. And yeah, it moves so fast that you can just see it moving because it's much closer. So it appears to move faster. But unfortunately, the forecast for that night is probably not going to be favorable. So I might have to cancel that stream. How far will it be from Earth when it's closest? If you mean this one that we're looking at here, 6.6 million kilometers. The other one I'm talking about, that will be only about 300,000 kilometers, or 0.3 million. So much closer than this one. Still moving the circle. All right, I think I might end the stream now. Let me just go back to my Sky view. Let me just check if my security cam on the telescope times out. Right. It's pointing to the west. Dome's still lined up with it. All right, so I think I'll end the stream now. Thanks everybody for watching, and check back if the stream on Saturday night is running. Wait a minute. Right. I got no UFOs. My UFO count is still 0. I still have not used the UFO counter ever. Thank you, Locrian. I take it you're in Japan. And so hopefully some of you can make it on Saturday. But as I said, weather forecast looks dodgy, so it probably won't happen. Okay, so bye, everyone.